This section of the course deals with choice under risk and uncertainty. It draws from Chapter 17 of the textbook.
Now, the thing that's important to realize about risk and uncertainty is that it's everywhere. Life is a series of gambles or risks. If you play the lottery, there's a chance that you might win the lottery, but there's also a chance that you might lose in the lottery. If you're selling corn, there's a riskiness associated with the price of corn that you might receive in October during the harvest. That price could be either high or it could be low. Before the price of corn is revealed by market forces, you don't know whether it's going to be high or low, and so there's an associated risk. More substantially, you might also think about the risk in your everyday life regarding things like contracting the flu. There's a chance that you might actually get the flu. There's also a chance that you might not get the flu. All of these risks are important because they impact the decisions that we make. And so this section of the course examines the effect of uncertainty on decision making made by consumers, but really largely by firms. In order to analyze decision making under uncertainty and when we're faced with risk, we need a way to describe and quantify risk. A particular event has a number of possible outcomes. The examples I described in the previous slide illustrate that. To describe how risky each outcome is, we need to quantify the likelihood that each possible outcome occurs. To describe the riskiness of a set of events, we use what's called probability. And probability is actually quite simple. It's just a number. It's a number between 0 and 1, and that number indicates the likelihood that a particular outcome occurs. For instance, when you listen to the weather forecast, the weather person will often say there's a 25% chance of precipitation. What that means is that there's a 25% likelihood that it will rain or snow during the day. It's just that simple. But those probability estimates and the numbers that we use to measure probability don't just come down from the heavens like rain. We actually have to estimate those probabilities. And there's two basic ways that we estimate probabilities. One is based on historical frequency. And this just is a count of the number of times that an event occurs divided by the number of times it might occur. So for instance, if you're in a community with 1,000 households, the probability that a household burns would be the number of households that burnt last year divided by the total number of houses. If there's 1,000 households in the community and 13 of those houses were affected by fire, we would say that the probability that a house burns is 13 divided by 1,000, or 1.3%. That's the historical frequency approach. And that's an approach that's used more often than not. Another approach is to use what's called subjective assessment. Now, what's important to recognize here is that it's subjective. It's what one person thinks the probability is. And that thought or their view of what the probability is may not necessarily be based on historical frequencies, but by their expertise in the marketplace. So in this instance, you use whatever information we have to form our best estimate or a guesstimate of the likelihood that an outcome will occur. To use these probabilities, what we do is we associate each possible outcome with an estimate of the probability or the likelihood that that outcome occurs. So really what we're doing is we're dealing with how to relate the probability of occurrence to each possible outcome. In the table, I've shown three different states of the economy, either a stagnant economy or an economy with slow growth or an economy with rapid growth, and the associated probabilities. So for instance, the stagnant economy has a probability of 0.25, and the way to interpret that is that there's a 25% chance for a stagnant economy. The second state of nature or outcome is slow growth, and the probability associated with the slow growth outcome is 0.45 or 45% chance. The table is quite informative because it actually shows the probability that we're dealing with. We could also summarize this information with a graph as well. Now, probabilities are very important because they actually help us understand something about what we might expect to happen. And to understand what we might expect to happen, we use a concept that's called expected value. And all an expected value is a weighted average. It's the weighted average of the event where the weights are the probabilities of each possible outcome. So if I have a particular outcome or state of nature, and there is associated with that a particular event or a particular outcome, such as I've earned money or I've lost money, the expected value is simply the weighted average of those events with the probabilities serving as weights. To make this a little more concrete, let's deal with what might seem like a silly example, but it's one that I think illustrates this quite well. Let's consider a promoter who's planning an outdoor concert. She'll make $15 if it doesn't rain, but will have to cancel the concert if it does rain. If she does have to cancel the concert, she's still going to have to pay the band $5. The weather forecasts call for a 50% chance of rain. So what we might be interested in knowing is what can the promoter expect to receive in terms of revenues or sales. To calculate that, we use expected value and we use what's called the expected value equation. This is a particular example of the expected value equation. And EV, which is our shorthand for expected value, simply equals the probability of it raining times the value associated with the outcome of rain. This will be the amount of money that the promoter either earns or loses if it rains, plus the probability of no rain times the value to the promoter of it not raining. So if we substitute the numbers in, what we'll find is that we end up with this equation. And so the 0.5 that you see, and I'm circling that with my mouse, that 0.5 is simply the probability of it raining. I've multiplied that by the value if it rains. Now remember, if it rains, they cancel the concert, but the promoter still has to pay the band for $5. And so the promoter is losing $5, and so that's why there's a negative sign here. So this is the monetary outcome for the promoter if it rains. We add to that the expected value if it doesn't rain. And so that's 0.5, which is the probability of it not raining, times 15, which is the amount of money the promoter will earn if it doesn't rain. If we do the calculation, what we find is that the promoter will expect to earn $5 regardless of the state of nature. So this isn't what actually happens. This is what they would expect to happen after you account for the probability of rain and no rain, and after you account for the different value that you will earn as the promoter depending on whether or not it rains or it does not rain. Now, so that's expected value, and that's very important in decision making with risk and uncertainty. What's also important, and some might argue even more important, are what we call measures of risk. That is, we'd like to be able to characterize the set of possible outcomes in terms of the riskiness associated with them. And there's different ways that we can do that. We could use a range of values to differentiate between the minimum and the maximum values. So for instance, in the previous example, the range would be -5 to 15. Variance is more commonly used, and all the variance measures is the spread of the probability distribution. It shows how widely spread the particular outcomes are. The advantage of using variance is that it doesn't depend on whether or not you have negative outcomes or positive outcomes. And the variance is actually quite simple to calculate as well. It's simply a probability weighted average of the square of the difference between the observed outcome and the expected value. Now just a quick word, there's a lot going on in risk and uncertainty, and so we're going to work through some examples in class to help illustrate these concepts. So if it doesn't seem like it's quite gelling with you yet, be patient. We will work through some examples to illustrate these because I think the illustrations actually help bring the concept to life. Let's go back to the example that we talked about before and use the variance equation to determine how risky this particular event is. So in this example, variance is simply a weighted average of the squared difference between the value with an outcome and the expected value. So in the equation, what I've written out is we've got the probability of no rain times the square of the difference between the value if there's no rain and what you would expect to happen, the expected value, plus the probability of rain times the square of the difference between the value if it does rain and the expected value. If I substitute in the respective numbers, I end up with this equation. 0.5 is the probability of no rain. 15 is the value to the promoter if it doesn't rain. I subtract 5, which is the expected value, and I square that difference. And the same thing in the second part of the equation. 0.5 is the probability of rain. There's a $5 loss that the promoter would realize if it does rain. I subtract from that the $5 expected value, and then I square that difference. If I go through with those calculations, I end up with a variance of 100. Now, by itself, the variance of 100 doesn't really tell you a lot, but if you had a couple of different outcomes that you're trying to compare, you would compare them on the basis of their expected value, but also on their variance. And the difference in the variance between particular options might actually sway the decision as to whether you prefer one option or another. So another way to think about this is to look at what would happen if the promoter faced some other option. If the promoter holds the concert indoors, she makes $10 if it does not rain, since the theater can't hold as many people as the outdoor venue. However, She breaks even if it does rain with an indoor concert. So what we would want to do is calculate the expected value under this alternative of holding the concert indoors. And again, all we would do is apply the expected value equation. It's 1/2 times the value if it does not rain, that's $10, plus 1/2 times the value if it does rain, and that's going to be a break-even amount, so 0. If we work through the calculations, the expected value is 5. Recall, the expected value if the concert was held outside was also 5. We can also calculate the variance by applying the variance equation. And that's all I've done in this line. I'm not going to work through the math, but I will note that the variance is lower with this particular option, that is the option to hold the concert indoors, and we see that it's only 25. So in this case, the indoor concert generates the same expected value, but it has much, much less risk. And that reduction in risk for some people is actually the thing that changes their mind regarding whether they would pursue one option or another option. So for instance, in this particular case, that might be the deciding factor in terms of whether the promoter wanted to have an outdoor concert or an indoor concert. Now, that's actually getting at the heart of the matter, which is how do you make decisions when you're faced with uncertainty or risk? For instance, you don't know whether the promoter would want to stage an indoor or an outdoor concert just yet. And in fact, to answer such a question, we need to know the promoter's attitudes towards risk. Do they like risk? Do they not like risk? Are they ambivalent towards risk? Those are questions that are very important in trying to understand how people make decisions when they're faced with any kind of risk or uncertainty. Now, to get at this, we actually have a different kind of expectation that we take account of. And this is called expected utility. And all this is a measure of, or a calculation that reflects people's taste for risks. And it shows how people's taste for risk affects their choice among options that differ both in value and in risk. If people made choices to maximize expected value, they would always choose the option with the higher expected value, regardless of the risk involved. But we know that people don't do that. Most people care about risk as well as expected value. And in fact, there's all sorts of evidence to point that it's not just expected value that matters, but it's the riskiness associated with particular options that individuals have to face that is the deciding factor. Expected utility is very much like expected value. It's a weighted average, only now it's a probability weighted average of the utility from each possible outcome. Now you might be wondering what I mean by utility, and we're going to talk a lot more about this during the semester. But briefly, the way to think about utility in this context is that it's the benefits or the pleasure that one enjoys from the amount of money that one has earned. So because of that, we often talk about utility of wealth or utility of income or utility of earnings. To put some meat on the bones, as it were, let's go back to the example of the promoter. In this case, expected utility would simply be the probability of no rain times the utility associated with the value of the money that I earned had it not rained, plus the probability of rain times the utility I get from the value that I earn when it does rain. If we substitute in some numbers, what you would see is that this expected utility calculation would be 1/2, or 0.5, that's the probability of rain, times the utility associated with the $15 I earn when there is no rain, plus 1/2 times the utility associated with the value that I receive when it does rain, and that's a loss of $5. And utility is a function. It's a mathematical expression, and it depends on earnings. And the shape of that utility function is very, very important when it comes to decision making with risk. In fact, that's at the kernel of the issue, is what is the shape of the utility function. Now, typically we assume that individual's utility increases with wealth. But how it increases determines how that person reacts to risky propositions. So the idea here is that more money gives you more utility, but the rate at which your utility increases as your wealth increases can determine exactly how you react to different risky propositions. Now, in the context of risk, a notion known as a fair bet becomes very important. And all a fair bet is a wager whose expected value is 0. So as an example, let's consider what we would call a fair coin being tossed. This is a coin where there's a 50% chance of heads or a 50% chance of tails. And in this example, let's suppose you win $1 if the flip coin comes up heads, and you lose $1 if the coin turns up tails. Well, the expected value of that is 1/2 times $1. That's the probability of it coming up heads and the amount that you win if it comes up heads, plus 1/2 times a loss of $1. That's the probability of a tails and the value to you if it does come up tails. If you work through the math, what you'll see is that the expected value is 0. This makes that wager or that bet a fair bet. Now, that becomes very important when we start thinking about the shape of the utility function and attitudes and preferences towards risk. And you'll see why in a few minutes. But to get at this, what we're going to do is introduce a term that's called risk averse. And a risk averse person is someone who does not want to make a fair bet. And the idea here is that they don't like risk. They don't like the variance. And the riskier an outcome is, the less likely they are to accept it. To illustrate this a little bit further, what I want you to do is to look at figure 6.1. And this is an example of a utility function for a risk-averse individual. And the idea here is that utility rises with wealth, but at a diminishing rate. And so the extra pleasure that one derives from each dollar of wealth is smaller than the previous dollar. So here, I've drawn it with wealth on the x-axis. You could think of this as earnings or income if you wanted to, and utility that you receive from your wealth on the y-axis. As wealth increases, your utility increases at a decreasing rate. Don't pay attention to the numbers that are shown there just yet, because what I'd like you to do is actually bring this slide and the notes with you to class on Wednesday, and we'll actually walk through an example that illustrates how we use the utility function to decide where one ought to consume and what activities one ought to engage in. And so that's going to be done in the example of a farmer. In particular, a farmer that has two options. One option is to continue growing and selling a crop in a conventional production system. And if you do that, or if the person does that, if the farmer does that, they receive $40 per acre with certainty. And her utility with that $40 per acre is 120 units. Her other option is to produce the crop organically. If she chooses to produce the crop organically, she receives $70 if the crop yields well, and that's $70 per acre, and she can get the desired premium for her product as well. However, her net returns drop to $10 if she does not get the higher price, which she assumes will happen with a 50% probability. So what the decision maker has to do is decide whether or not to continue producing conventionally or to switch over to organic production, recognizing that the risk is associated with the premium that you might receive in the marketplace. So be sure to bring figure 6.1 with you to class on Wednesday, and we'll work through this example to illustrate how decision making with risk and uncertainty can be undertaken with some fairly simple calculations. That's all for now. We'll see you in class.